Today has not been my day for recording videos. But the secret is don't give up. Just keep working and keep doing it until you get it right. And don't let technology stop you. So this is the second part, or part two of videos. I have the regression part, which this is in a machine learning video. Now, linear regression or multiple regression is very, very common in the business intelligence world, or in the business world in general. Most programs can do it. I know Tableau can do a couple different types. Power BI can do it. R can do it. Python, Excel. Yeah, Excel can do it. SPSS can do it. SAS. I mean, literally everything can do a regression. The issue is, should you be doing a regression? Have you met the assumptions? I've taken multiple classes and learned regression through a bunch of different classes and through my job. And I can tell you probably at least once a month, I find somebody using regression, linear regression, multiple regression, and they're using the wrong model, or it should not be used in the data set they have. So that's why I'm going to try to focus on assumptions. So we're going to cover, again, the definitions and cases, simple LR, multiple LR, and then the assumptions of linear regression. And I cannot stress this enough that please think about the assumptions. So what would I consider a win for this class, for this single session? Not including machine learning, but for regression. I don't really care if you know the math formulas. I don't care if you know, no. What I want is in 3 months, 1 year, 5 years, 2 years, when you're doing a linear regression project or a model or something, that you look at it and say, hey, you know what? I can't remember linear regression assumptions. Let me Google them. I'd rather just be safe and let me Google the linear regression model. Well, hey, multicollinearity, I don't know what that is. Let me Google it. Oh, you know what? That doesn't apply to me. I'm good. So if you do that, sorry, my dog is just attacking me today. If you do that, I would consider that a win. Okay? So before we get into that, it is vital that we understand what an independent variable and a dependent variable is. I have a video I'm going to show you here about correlation here in a second, but what is an independent variable? Where do you put it on a graph? Does it go in X or Y? What's a dependent variable? If I ask any of you in 6 months from now and you're working on a project and I happen to see you, hey, what's an independent variable? What's a dependent variable? You should be able to say, hey, this is what it is. And once you get to be really comfortable with that level of independent and dependent variable, it will help you with your graphing, it will help you with the visualization, it will help you with your linear regression or multiple graphs. Another way to think about independent variable and dependent variable is cause and effect. And this is not through science, it's just through everything that we work on in business intelligence. The independent variable is the cause. Am I spending more money in marketing? Did I change the color of the paint? Obama ran a campaign where he changed his picture from color picture to black and white picture. The effect was, how much in donations did he get? The different pictures cause a difference in donations. The story is much nicer than I remember. The most expensive A/B testing campaign ever done, an online Obama campaign. Okay, big experiment. Now, this is combination 11. So they go through all this math, and they say that this contributed, this change, let's say $60 million, say actually results in about $200 million in additional revenue. So if you truly understand your independent and dependent variables, it will make life so much simpler. Okay. Here's another example of it. Independent variable is the amount of liquid, or no, maybe not the amount, the type of, well, it could be wrong, but the type of liquid I use to water a plant. So I want to see if these 5 different liquids have a difference in how much my plant grows. So I'm going to take the first plant and I'm going to say, hey, I'm going to feed it Dr. Pepper. Second plant, well, I'm going to give it milk. Third plant, I'm going to give it water. And the fourth plant, I'm going to give it water with Miracle-Gro. Those are all my independent variables. The dependent variable is a height. How high did the plant grow? So my controlled variables, let's think about this. I want to ensure that each one of my plants get the same amount of light each day. I want to make sure the same type of soil. I want to make sure the same type of plants are on all 4 or 5 plants. Okay? So it's important that you understand independent and dependent variables through business, through biology, through anything that you're doing, data science and business intelligence and data analytics. These are key concepts. When we do graphing, the independent variable generally, not all the time, but generally 99% of the time, 95% of the time, goes on the bottom. The dependent variable is your y-axis. X is independent, y is dependent. Now I have a short video I'm going to show you about correlation and causation before we get to linear regression. And while this video is 7 minutes, and I would never really normally spend 7 minutes of my lecture going over correlation and causation, it shows you how important this topic is. Because too often people use correlation equals causation, or they do something else, and there's cognitive biases in it. And we talked about cognitive biases, 2 or 3 weeks ago? So that's why I like this particular video I'm going to show you. Let me actually get it up here. Okay, I think it does a great job of explaining the two. So let me see if I can zoom in a little bit. And okay, let's see if this works. Hit play.
Correlation does not imply causation. You've probably heard this many times before, and for machine learning people, this is prediction does not imply causation. So the example here is that, say you are looking at data of people who sleep with their shoes on and wake up with headaches. And it turns out that most people who sleep with their shoes on wake up with headaches. Most people who don't sleep with their shoes on don't wake up with headaches. The two are strongly correlated, strongly associated. You might think, oh, okay, I probably shouldn't sleep with my shoes on because I don't want to wake up with a headache, that it's a cause. But, what if in your data you also have information that most of the people who were going to sleep with their shoes on were also drinking pretty heavily the night before? And those same people were the ones waking up with a headache. Then you might think, oh, okay, the only reason that we're seeing this association between the two is because there's a common cause, which is drinking the night before. And there's sort of 2 ways to resolve in your head why shoe sleeping is so strongly correlated with waking up with a headache. And the first is that, consider 2 groups of people. The ones who went to sleep with their shoes on, so that's the shoe sleepers, and the ones who went to sleep without their shoes on, the non-shoe sleepers. These 2 groups of people differ in a very key way, and that is that almost everyone in the shoe sleeping group drank the night before. Almost everyone in the non-shoe sleeping group did not drink the night before. So the key way is sort of think about the average number of people who drank the night before. It's just a completely different number. And that kind of explains why we can't look at these 2 groups and deduce some causal effect from them. The groups are not comparable. You would want that the groups to be the same in every way except for the treatment, whether or not they went to sleep with shoes on. The other way is confounding. So because we have this common cause, it confounds the effect of shoe sleeping on waking up with a headache. And graphically, you should visualize it this way. There's this confounding association that is running between shoe sleeping and waking up with a headache. And that's the association that we observe. This is in contrast to causal association, which would be a sort of directed path from shoe sleeping to headache. the association that we observe, the total association, is a mixture of these causal and confounding associations. And correlation is just one type of association. Association here is just a synonym for statistical dependence. And correlation is technically a measure of linear statistical dependence, but people frequently use it to mean statistical dependence in general. But to avoid the confusion, we're just going to use the word association rather than correlation. But yeah, just let that sink in your minds. If you were to measure correlation, or any measure of association, you would be looking at a mixture of causal and confounding association. And that additional confounding association is why correlation does not imply causation. So many of us have learned that correlation does not imply causation, but that doesn't stop us from using this heuristic all the time. Correlation equals causation is actually a cognitive bias. Okay, so in this example, where shoe sleeping is associated with a headache, you could actually just replace shoe sleeping with star, just with anything, say. So just anything associated with your headache. And this star could come from a variety of different places. One is the availability heuristic, which is another cognitive bias. And what does the availability heuristic say? It roughly says what will come into your mind, what star will come into your mind, is just whatever is most readily available in your mind. So for example, if you recently read, say yesterday, that caffeine is associated with headaches, then you might think, oh, it's because I drank a cup of coffee earlier today. That's why I have a headache. Even if, say, 2 years ago, you read an article saying caffeine is not associated with headaches. That's just not nearly as available in your mind. So say you want to explain why you have a headache. You have a headache and you're saying, why do I have this headache? How can I not have a headache in the future? The way we might do this is come up with some star via the availability heuristic or motivated reasoning, which I'll talk about briefly. And given that that star is associated with our headache, we'll say, okay, that explains the headache, using the correlation equals causation cognitive bias. And motivated reasoning here is that we have some worldview that we want to come up with reasoning to justify our worldview. So an example of motivated reasoning in this case is, say that I don't enjoy spending time with my in-laws. I might be motivated to attribute my headache to the time that I spent with my in-laws earlier that day. I might say, okay, I got a headache because I spent time with my in-laws earlier today, so I probably shouldn't hang out with...
Okay, and I know, like I said, that's a little, I don't want to say off topic, but it's always important to remember, okay? That correlation does not imply, relate to causation. And this can go into things like, hey, why can't we prove that cigarette smoking causes lung cancer? There's that spiritualist correlation site that shows, hey, A equals B, just all types of crazy things. So just because two variables move together does not mean one causes the other. And remember, positive and negative correlation, they don't have anything to do with good or bad. A positive correlation means that X moves and Y moves in the same direction. They both go up, they both go down. And that's important to remember too. A positive correlation means, hey, if the number of rooms go down, the price of the house goes down. A negative correlation does opposite. One goes up and one goes down. One increases and one decreases. And neither one of these are good or bad. It just really depends on your data set. .14 minutes. Okay, so two major types of linear regression. Simple, A and B, tracking two things, and multiple. Again, I'm not going to go into a whole lot of math. In the Python, maybe we might get a little heavier. But again, when Tableau, you're not going to see the math behind Tableau. Drag two things on Tableau, and boom, it's going to do a linear regression for you. So that's why I'm not going to get a lot into the math. Well, once let me show you some of these things too. So real quick, if you guys are interested, Min Young Kong in the CS department, he teaches a machine learning class, and he has some great notes and information on the mathematics of linear regression. I took his class. I loved it. If you're really interested in linear regression, this is, he's got a lot of great stuff. I know UNLV, I think in the statistics class, teaches a class, or maybe it's public health, on linear regression. This is a note from a professor called Chad Cross. He's got some great stuff on linear regressions. I mean, you see that we're getting into the math on linear regression instantly. Multiple linear regression, multiple regressors. And then binary, I don't know if you went into polynomial or other types of regression, but there's a lot of great ways to learn linear regression. And again, I don't want to focus this class on that. I'd much rather you guys say, hey, what's linear regression? Run it through and make a report, then think to yourself, is this the right tool for linear regression? Okay. So let me switch over here, Chrome Video. It's simple multiple linear regressions. It's just the number of variables we use. It's simple. Okay, so assumptions. And that last one you saw something called line. Line is, and I'm going to go into each one. I'm going to go into most of these here in a second. But the line assumption is L-I-N-E. There's a linear relationship between your variables. There's independent observations and errors. It's a normal distribution, which I guess normality, but there is normal distribution. And there's equal variance. So actually here, let me look at this. Check this out. So there we go. So linearity. What is that? That's number one. That the X and Y have a linear relationship. And don't worry, I got more on this. So if this guy has confused you, don't worry. Homoscedasticity. There's equal variance, equal error, equal residual. Okay, that here's X and Y, and that these to this line are equally distributed at the bottom and at the top. As we move out to the right, our error is basically equal. See how this is much greater? These are probably the two big ones, and maybe outlier check that I see a lot. Yeah, because one outlier can really throw things out on linear regression. Multiple outliers can make it even worse. So let's go into each one of these real quick. I'm only going to cover 3 or 4 of these. Some of these are for simple or singular linear regression. Some of these are using multiple regression, and I'll talk about that towards the end. Well, I have another couple slides to say, hey, here's a ridge regression. Here's what the assumptions are. Here is a polynomial regression. Here's what some of the assumptions are. So linearity, that was that first one we saw. The relationship between X and Y is linear. The relationship between the number of rooms in a house and the size of the house is linear. So if you predict the house prices based on the number of rooms, the assumption implies that increasing the number of rooms by 1 unit will consistently change the price, regardless of the current number of rooms. Independent. So residual, when you hear the word residual, okay, the residual is the error. So it's a different, actually I think on the next slide. There's a difference between predicted and observed. Okay. If we're predicting monthly sales price and advertising we spend, the error from 1 month should not predict the error in another month. Residual. See the difference between observed and predicted. And the reason I really want to drill in residual is because often people think they use that word, I don't want to say incorrectly, they don't understand what residual is. It's just error. Okay, that's an easy way to think about it for now. If we're predicting salary based on years of experience, so if you have more experience, you should have more salary. If we're predicting salary based on years of experience, the variance in salary should be roughly the same for all levels of experience. For some reason, guys, today my allergies are killing me. normalcy of errors. So you can do this with Shapiro-Wilcox. I think that's how it Shapiro-Wilk test. Okay, you look at the skewness and the kurtosis of, I guess, yeah, skewness and kurtosis of distribution. But in a nutshell, the model predicting test scores. So we're trying to predict test scores based on the number of hours studied. The distribution of errors should be a normal distribution. Okay, now that's not always the case, because sometimes some things have like a one-way skew. Okay, income maybe, poverty level, things like this might not have a normal distribution of errors. So we have to be really careful. So we use this one more in multiple linear regression, but the independent variables are not highly correlated. So this is where we do a heat map. We can do a couple different methods to test to see if our independent variables are correlated. If I'm doing, okay, so if I'm doing, I want to predict if our sales are affected by marketing. Okay, so hey, it's a simple question. A friend of mine's interviewing, that's why I just thought about it. A friend of mine's interviewing for a data science job in a marketing department. And it's surprising because I have a bunch of data scientists in this marketing department. But the question is, hey, the more money I spend in total marketing, does that increase my total sales? That's fine. Well, I throw in marketing, total money spent in marketing, which includes TV, then also TV sales or TV marketing budget, radio budget, print budget, internet budget. Does that relate to sales? Well, now we have a problem, because my total sales budget also includes TV budget. Since they're highly correlated, I'm not going to be able to isolate individual variables. Okay. This is time series related more than anything else. We'll see in a time series model predicting stock prices, the error from one period should not predict the error from another period. I think that makes sense. Additional regression assumptions, additivity. So yeah, those are the ones I thought about over the last couple of weeks or so. The ones I saw that were errors. Now, sometimes when you have these violations of assumptions, you can use a different model. Sometimes with outliers, you might have to transform your data. Sometimes there's nothing you can do, and you're just going to have to declare, hey, this is not a very good model. Okay, so just because there's a violation of the assumption doesn't mean you just get to go home and walk away and say, oh, that's not going to work. If I have something, you might be able to move to ridge regression. You might be able, well, actually, let's go into that. Okay, so I still have to work on this. So we commonly use, or a lot of times we use simple, linear, ridge, lasso. I haven't used elastic net recently. Polynomial I use once in a while. Logistic regression we use. So let's go into a little bit of type. So linear regression, A and B, X and Y. Predicting a continuous variable outcome from one or more predictors of variables. Actually, well, I guess since we didn't say it's not multiple. Predicting house prices based on size. Predicting house prices based on location. Why is my assumptions wrong? So the assumption you just read, should go in here. So I guess I just copied and pasted it wrong from some of my notes. So bad me, mea culpa. So there we go. Let's try to see if my next one's right. Oh, there we go. Multiple linear regressions. Basically, with multiple independent variables, predicting a person's weight based on height, age, and diet. So I'm using 3 things to predict one thing. Okay. Polynomial regression. Now I know Tableau does this one, I believe. Actually, let me check really quick. I'm pretty sure Tableau does this. When the relationship between the independent variable and the dependent variable is nonlinear. It's a polynomial relationship. It's this. Predicting the growth rate of crops based on temperature, where the growth rate may increase up to an optimal temperature and decrease thereafter. Look, I should have a space here. Ooh, my slides are not doing good today. But I guess that makes sense. Let's go to another one, ridge regression. So ridge regression is, is lasso next? Yeah, lasso is next. Ridge and lasso are relatively common, and they should be used probably more than they are. Okay, so when we have multiple regression, you can add things that don't really add value, and your regression will be a better model, but it's not a more accurate model. Because the way traditional regression works, the more you add to it, the better predictor it's going to be. But again, it's not always accurate because some things just don't predict correctly. And it's just the way the math works. Okay, so because there's no penalty for adding additional regressors. So one thing we can do is we can use a ridge regression. So if we have 2 or 3 things, ridge regression kind of says, hey, you know what? Just because you're adding another thing, I'm smart. I know that you're adding something else. If it doesn't add to my model, I'm going to penalize you for it. I guess that kind of makes sense. You know, it penalizes the sum of squares, basically. And so does lasso regression. They both penalize multiple regressors. Where multiple regression just uses the least sum, ordinary least sum. Sorry about that. So just kind of remember that if you have multiple regressors that may not add a whole lot, you know, that they don't have the collinearity. If they do have collinearity, technically speaking, I guess you want to use ridge or lasso. Okay. So if you have like 5 variables, for example, lasso will select maybe the best variable, the feature of the best variable. Say, hey, you know what? Use this one. So lasso is good when you have. Let me go over to the next one. See what I say about lasso. Lasso is really good when you have things that are, I guess, similar. When your covariants are similar, when your regressors are similar. Yeah, I guess, you know, when your collinearity is high, you know, you want to use ridge or lasso. And it depends on kind of how they are high, is what one you want to use. Adds penalty term to the loss function. So, what else did I include here? Logistics. So this is just a binary assumption. You know, I don't really use this one too much. Maybe once a year. You know, this elastic net regression used to be really popular, and I just don't see it as much. So let's see what else we got here. And again, there's more types. And believe it or not, Cox have been using a little bit more than normal. I used Poseidon distribution a couple days ago. So there's just, like I said, there's a lot of different types of regression. So I even put a takeaway slide. And again, I want you to remember that the takeaway from this is, hey, where do I have my overview? I'm going to go back to that one slide. This. When I'm doing a linear regression model in 3 months, 6 months, 6 years, what do I want you to remember? You know, I want you to remember to go to Google. What are the assumptions of linear regression, and how do I know if I am breaking them? Okay. And oh, I clicked one. Okay. So this is so important because even as an editor on a paper, as a reviewer on papers, I've seen last year and the year before, especially with COVID and other things, I've seen countless papers that use the wrong type of regression. Business intelligence, I've seen wrong types of white sheets that use the wrong type of regression. And it's hard because, again, regression may get you in the area, even if it's the wrong type, and then you go, hey, look what I found. If we do this, we're going to get to this goal. And that's just not always that's not always the case. So, oh, look at this. I didn't even know this. Oops, go away. Go away. Another thing's popping up here. Oh, nope. I guess continue reading. No, nobody wants to sign in. So, again, please take the time to think about your regressions. Hey, I have multiple things that are related. I'm going to use ridge. I have two simple variables. I'm going to use linear regression. When I'm doing linear regression, all my data is my X and Y. Are they linearly related? Are they normally distributed? Are my errors, are they normally distributed? It's not, a QQ plot that's all weird. QQ plot. Do I have a QQ plot that's bad versus good? Bad, bad, bad. That's not, you know, that's not looking the way it should. Okay. Your QQ plot basically should look, like this. Something like this. Okay. Just looks at your error versus basically a line. It says, hey, this is, yeah, you have a little bit more errors here and a little bit here. That might be a bit of a concern. But what you don't want is like this. This would be bad if you had a QQ plot. This would be bad if you had a QQ plot. I would say don't use a linear regression if you had that. So, any questions on linear regression, please let me know. Please watch the machine learning video. I'll get that uploaded probably tomorrow morning. And have a good weekend.